Welcome to Mac 2311 for engineers, exam number 4, free response number 1. This question has several parts to it, so it's going to take a little bit. They go ahead and they start off by giving you this function, ln of x, and they give you the interval 1 to 9. So they even give you the graph of the function here. The very first part is they want you to go ahead and use left endpoints and use 4 subintervals to approximate the area from 1 to 9. So if we're going from 1 to 9, we know that's a distance of 8. It's just, this is like your A, this is your B. B minus A gives you 8. And then we have 4 subintervals, so in that case your n is 4. So 8 divided by 4 is 2. So we know each subinterval will have a width of 2. So we can go ahead and break this up into 4 little pieces, and then you can see this would be 3, this would be 5, and this would be 7, because this is all just adding 2 each time. And you get from the 1 to the 9. So then what happens is we want to go ahead and we want to draw a picture first off, and then go ahead and actually find the approximation of the area from 1 to 9 for this curve here. And we're using left endpoint. So that means we just want to draw rectangles that on the left side connect with the function. So the very first rectangle you'll see is actually just going to be at 0. The second rectangle will be up there. The third will actually come up and hit there. And the fourth will come up and hit here. So from the picture you can definitely see it's going to be an under approximation because we actually have all these gaps we left. So we need to just go ahead and find out what all of this area is going to be. And then we'll be done. So how do we find it out? Well, it's just the area of a rectangle is width times height, and then if we add up all 4 of these rectangles, then we have our approximation. So what we can do is, we know the width are all going to be 2, so we can just simply go ahead and say 2 times, and go f of our left endpoint, because f is actually what the function is going to be equal to, the y value, and that's like our height in this case. So it's going to be f of 1 plus f of 3 plus f of 5 plus f of 9. So you can see that 2 times this would give you the area of the first rectangle, 2 times that, area of the second, and so on and so forth. So f of 1, you can see is ln of 1, which is 0, which is what we anticipated, so that would be a 0. Then you'd have ln of 3, plus, and then ln of 5, and then ln of 9. You just want to leave it like that for the time being, because we don't know what ln of 3, 5, or 9 are. Then you can go ahead and multiply the 2 through it. So your answer is just going to be 2 times, so we can actually just erase this part right here. And say our answer is going to be 2 times this, and that's just some number. That's our approximation. So that's it for part A. This value right here. So then the second part says, okay, if we want to actually take the integral and find the exact area from 1 to 9 of this function, what would the Riemann sum look like? And they don't want you to actually evaluate the Riemann sum, they just want you to fill in the blanks, the missing pieces. And they give you limit and sum. So we need to go ahead and actually fill in the little notation here, and then actually put in where a function should be. So underneath the limit, it should be n goes to infinity, because we want to actually sum up an infinite number of subintervals, an infinite number of rectangles. The sum is always just going to be I equals 1 to n, because this is basically it's a little timekeeper, a placeholder. It tells you which rectangle you should be at. And so you start out from the first rectangle and go all the way to the nth rectangle. So this is always going to look like that. Now this is what changes. What should be here should be f of xi star times delta x. What is delta x and what is xi star? Well, we know that delta x should just be b minus a over n. That's just telling you the width of each rectangle. So it would be your final minus your initial, so 9 minus 1 gives you the 8, but divided by n. So it's basically the same formula we used to find the width of each rectangle. It's just now we didn't set n equal to 4, we're actually just going to leave it as n, because eventually we'll take the limit as n goes to infinity, because we want an infinite number of them. So our delta x in this case is just going to be 8 divided by n. So now what's xi star? Xi star should be a plus I delta x. That's the formula. And that makes sense because this actually tells you what endpoint you're at, or what rectangle you're at. Because you start off at A, so that's at the very beginning, and then delta x is the width of each rectangle. And I was saying, was that like little counter that's just moving us along. So when I is equal to 1, that's the first rectangle. and then once you go ahead and increase I to the next value, say to 2 or 3, then you go over that many rectangle widths worth. So you're at A, and then you go over to the first rectangle, second rectangle, so on and so forth. So this is your equation. Now in this case, A is equal to 1, and I is just I, and we know delta x is 8 over n. So what goes here would be f of xi star, and f is ln of x. So you'd want to say ln of, and xi star was going to be 1 plus I times the delta x, so 8i over n, and then times the delta x. So it's just going to be 8 over n. Because this guy right here is going to be our f of xi star, and this guy right here will just be our delta x. And that's just the formula. You have to have that memorized. Okay, so and then this is what it should look like. And then we're done. They don't want you to go ahead and evaluate this, and you really couldn't evaluate it. It'd be pretty difficult. So the next part is jump over here. They go ahead and they say, prove that this function here is actually an antiderivative of the original function. So to prove that something is an antiderivative, all you have to do is differentiate this and see if it gets you back to there. Because the derivative and antiderivative, they're opposites. So if we derive this, you can see this is going to be a product rule. So it's going to be first derivative of the second, which is 1 over x, plus second derivative of the first, and the derivative of x just goes to 1. So we have this. And then finally you go minus 1, because the derivative of x just takes you to 1. Then you can see this x will cancel out that x, just leaving you the 1. But 1 minus 1, they cancel out perfectly, and you're just left with that single ln of x, which is what our original function was. So this must actually be an antiderivative. Okay, so that's nice. So we've proven that. That was part C. So that's done. And then the last part, part D, is they want you to go ahead and use this bit of information along with the original function that we had and actually solve out the integral from 1 to 9. Because if we just want to go ahead and take the integral of ln of x, we don't really know how to take that. We know the integral of 1 over x gets us back to ln of x, but to actually integrate ln of x, we're not sure how to do that yet. But we just proved that this guy right here was an antiderivative. So that means if we integrate ln of x, we should be getting this. So we can go ahead and say this is just going to be x ln x minus x, and then we just need to evaluate that from 1 to 9. So we've already done the integration. So then you can go ahead and plug the 9 in, so you get 9 ln of 9 minus 9, and you can plug the 1 in, and ln of 1 is going to go to 0, and then you have a minus 1. So you have another minus 1, but it's top minus bottom, so it should actually be plus. It should be minus the negative 1. So then you can combine these, and you get 9 ln of 9 minus 8. And that's going to be your final answer. So to recap real quick, they gave you this function and those endpoints. They gave you the graph of it, and they want you to go ahead and fill in the little rectangles with left endpoints touching. So we did that. They each had a width of 2, because this was a total width of 8, and we divided it by 4 into 4 subintervals. So then we drew the picture, and then to go ahead and get our approximation, you need to go ahead and go width times all the heights summed up. How do you get the height? Well, you go ahead and plug in your left endpoints into the function, because that tells you what your y is, what your height is. So we said f of 1 plus f of 3 plus f of 5 plus f of 9. F of x is really ln of x, so you end up getting this value out here. We can just leave it like that. We don't know exactly what it is. It's just some random decimal. So then the next part said, okay, if we want to find the integral from 1 to 9 of the function, what's the Riemann sum of this? So we need to fill in all the spots that were blank. So we went ahead and put the n goes to infinity, the I equals 1, the n on top, that's just standard procedure. Then here should be f of xi star times delta x. What are those? Well, delta x, we said, was b minus a over n, which gave us 8n, or 8 over n. And then xi star was a plus I times delta x. So you just went ahead and filled that in and plugged it into the function. And you get this expression here. And then we're done. We don't have to evaluate. So then part C was prove that this was actually an antiderivative of the original function. So we just went ahead and said, okay, we'll derive this. If it actually is an antiderivative, we should get back to the original function. And we did. So it worked out. The last part was going ahead and actually integrating from 1 to 9 of the function. So taking the integral of that, well, we already know the antiderivative of it. So all we have to do is just evaluate it from 1 to 9 of that guy right there. So you just go top minus bottom, it ends up giving you 9 ln of 9 minus 8. And that's all there is to the problem.